when we compare chloroacetic acid with dichloroacetic acid, then here due to presence of two chlorine, this have a stronger electron withdrawing inductive effect. Here only one chlorine is there which have the less electron withdrawing inductive effect as compared to this molecule. Due to that, it decreases the electron density far more as compared to this. That's why this dichloroacetic acid is more stronger acid than monochloroacetic acid. Again, we add one more halogen, and when we compare the acidity of this molecule, then these 3 chlorine have the more stronger electron withdrawing inductive effect as compared to dichloro and monochloroacetic acid. Due to that, electron density is decreases at the carboxyl center, and this becomes the stronger acid, more stronger acid. And when in all these molecules we compare, then trichloroacetic acid is stronger acid, then dichloroacetic acid is stronger acid, then fluorochloroacetic acid, fluoroacetic acid, then chloroacetic acid, then bromoacetic acid, then iodoacetic acid, and then acetic acid. So then in all these molecules, acetic acid is the bigger acid, and in all these molecules, trichloroacetic acid is the stronger acid even than the fluoroacetic acid. And when we compare trifluoroacetic acid, then trifluoroacetic acid is still more stronger acid as compared to trichloroacetic acid, because fluorine is more electronegative than chlorine. So electron withdrawing inductive effect of fluorine is more stronger as compared to trichloroacetic acid. Now further we will discuss one more example. As you know that the inductive effect is decreases as we go away from the electronegative atom. Now this is the best example for that, when we have this 2-chlorobutanoic acid, three-chlorobutanoic acid, and 4-chlorobutanoic acid, and when we compare the acidity of this molecule, then the chlorine which is present at the second position, it is more near to the carboxyl center. That's why this will have stronger effect. So chlorine withdraw the electron from this carboxyl center, and so that the electron density at carboxyl center is less as compared to these two molecules, or as compared to its counterpart butanoic acid. Due to that, this will show this become stronger acid. But when this chlorine is shifted to the neighboring position, then the distance of this chlorine from the carboxylic center is increases. And as we know that as the electronegative atom go away from the center, then the inductive effect is decreases. Now see, chlorine withdraw the electron from this, it withdraw the electron, and this electron will go toward the oxygen. Due to that, inductive effect is decreases. So electron density at carboxyl center is more as compared to this center. So that's why this is weaker acid as compared to 2-chloroacetic acid. And further, if we shift chlorine at fourth position, then the chlorine is far away from this carboxyl center, so that its effect is from this position to this position to this position, and then the electron will go towards this side. So then this is far away from this carboxyl center, its effect at the carboxyl center is negligible. That's why the electron density at carboxyl center is remain as it is. Due to that, this is still weaker acid as compared to this 3-chloroacetic acid, which is still weaker acid as compared to 2-chloroacetic acid. So that means, you remember, if the distance of the electronegative atom is increases from the center, then the acidity is decreases. Now come to another example. Now come to the basic molecule. Ammonia, then methylamine, or this is also called as the primary amine, then secondary amine, or this is also called dimethylamine, and tertiary amine or trimethylamine. You know that the nitrogen containing compounds, primary amine, secondary amine or tertiary amines, are basic in nature due to presence of lone pair at the nitrogen. And this nitrogen already have its electron pair, and it is electronegative also. Due to that, its electron withdrawing inductive effect, it withdraws the electron from its neighboring atom. When it withdraws the electron from its neighboring atom, it becomes electron rich. And if this center is more electron rich, then it becomes a stronger base. So then we will compare all these four molecules in the form of inductive effect and then decide which will be the stronger base. And you remember the nitrogen which is more electron rich, that becomes stronger base. Now we will decide which will be the stronger base. Now here three hydrogens are there. All these three hydrogens donate the electron to the nitrogen, that make the nitrogen electron rich. Now here one molecule is methyl and other is hydrogen atom. So then when we compare this molecule and this molecule, then as compared to the hydrogen, methyl group will donate more number of electron. It make this nitrogen more electron rich as compared to hydrogen. So here two hydrogens are there, they donate the electron, and here one methyl group is there. So methyl group give the more number of electron to the nitrogen. That's why this methylamine is more electron rich as compared to ammonia. That's why this is stronger base as compared to ammonia. Now come to the third molecule. Now here two hydrogens are substituted by two methyl group, and both the methyl groups are electron donating. They donate the electron to the nitrogen. They make the nitrogen more electron rich as compared to methylamine, because here only one methyl group is there. Due to that, this dimethylamine is stronger base than methylamine. Again, when we shift to the third molecule, then in this third molecule, all the three methyl groups, all the three hydrogens are replaced by methyl group, and all the three methyl groups donate their electrons to the nitrogen, and that make this nitrogen more electron rich as compared to dimethylamine, methylamine and ammonia. That means when we apply this inductive effect concept, then the tertiary amine or trimethylamine is the stronger base than all these remaining molecules. But the stronger base is this dimethylamine, because here not only the inductive effect is applicable to determine the stronger base, but when the ammonia molecule is protonated, then after protonation, how many water molecule or the solvent molecule gets stabilized? That protonated cation of ammonium ion, that can be stabilized, that molecule. So here when NH3 is protonated, that get converted into cation ammonium ion, and this ammonium ion is solvated in water by water. They get attracted by the water from all sides. So four water molecules are stabilized to this ammonia molecule. Now when we consider this secondary amine, which after protonation get the positive charge, then here three hydrogens are there and one methyl group is there. So then here one water molecule, second water molecule and third water molecule. In this way three water molecules are stabilized to this molecule. Here four water molecules are stabilized. When we compare this, then here NH, CH3, CH3 plus here two water molecules stabilized. Here also two water molecules get stabilized. So then, as compared to these two molecules, this stabilized by two water molecules, and at the end, when tertiary amine is get protonated, then that have the only one water molecule that get stabilized. So when we combine both these two concepts, then according to inductive effect, trimethylamine is highly stable, and according to solvation effect, this ammonia molecule is stabilized. So when we have to combine these two concepts, and when we combine these two concepts, then in that this molecule is strongly basic, as well as the two water molecule get solvated or stabilized by this molecule. Due to that, this secondary amine become more stable as compared to tertiary amine. But here in ammonia molecule, so very negligible inductive effect is present. That's why this nitrogen do not have that much electron density that this and this nitrogen will have. And out of these three molecules, this tertiary trimethylamine is having the higher electron density as compared to dimethylamine. But when we consider the solvation effect, then dimethylamine is more stabilized as compared to trimethylamine. That's why this dimethylamine is basic in nature. And this is considered in the form of this molecule. But when we consider trimethylamine, triethylamine, CH2, CH3, CH2, CH3 and CH2, CH3. In triethylamine, the nitrogen, the geometry of ammonia is pyramidal. Here three hydrogens are there and nitrogen is exactly at the apex. When all three hydrogens are replaced by bulky group, that means ethyl group, then CH2, CH3, CH2, CH3 and CH2, CH3. So from all sides ethyl group is there. Nitrogen is electron rich by inductive effect, but due to presence of bulkier group, any other molecule which needs that lone pair from the nitrogen could not reach at this center due to steric hindrance of these three methyl group. So that's why when we compare this molecule with respect to this trimethylamine, then this also have one more effect, steric effect. Due to that steric effect, even if this nitrogen is electron rich, highly electron rich, but it could not give the electron pair easily due to the three bulky group, due to steric hindrance available. That three bulky group could not allow the other molecule to take that lone pair. So that's why even if molecule is electron rich, molecule is ready to donate the electron pair, but no any other atom reach to that center to take that electron pair due to steric effect. That's why this is weakly basic. But if we remove one ethyl group by hydrogen, then this becomes stronger base, because when you consider this diethylamine, then ethyl group is here, Now from this side steric hindrance is there, from this side steric hindrance is there, but here hydrogen is there, from this side no steric hindrance is there. So molecule come from this side, take the electron pair, react with this molecule and convert it into product. So then that is also another reason why this secondary amine or dimethylamine or diethylamine is stronger base, because these have less steric hindrance as compared to trimethylamine. Due to that, always in solvent or polar solvent, this dimethylamine or secondary amine is stronger base than trimethyl or tertiary amine. But when we use non-polar solvent, like chlorobenzene, carbon tetrachloride, then in that non-polar solvent, basicity will compare. Then in non-polar solvent, trimethylamine is a stronger base because there is no solvation effect. This molecule could not solvate in a non-polar solvent, so that's why that have only inductive effect. And due to that inductive effect, the highly electron rich center is this tertiary amine nitrogen. Due to that, this nitrogen is ready to donate the electron pair. But if this molecule is bulkier, then due to steric hindrance, this molecule is weakly basic as compared to secondary amine. Because in that case also, the steric hindrance could not allow the other molecule to reach to the nitrogen center to take that lone pair, even if you use non-polar solvent. So that's why the possibility of the strong basicity is always goes toward the secondary amine. But when we consider in general example, out of this primary, secondary, tertiary amine which is more basic, then we will have to give the answer tertiary amine. Again, one more example we will consider. When this is the molecule CF3, then here now you see 9 fluorines are present, and fluorine is the highest electronegative element present in periodic table. So all this fluorine will withdraw the electron from all sides, and due to that the only one nitrogen which have the electron rich center donate its electron toward the fluorine. So that means here electron density at the nitrogen is decreases. So no electron is available on the nitrogen, even if the electron pair is available, but due to electronegativity, the inductive effect is reversible, and due to that, this molecule is negligibly basic in nature. Almost this is non-basic in nature. This is about the inductive effect. This is the one of the factor which affect the acidity and basicity of